Hello, we are going to take a look at some sample calculations, and this actually corresponds with the sample calculations worksheet. Um, Problem B, now technically they give you the E standard cell in B, but we're going to talk about how to find that just as to start us off, and then we're asked to find delta G standard, so let's do that. So first things first, we've got this balanced equation given to us for the redox reaction. If we took a look at the half reactions, if we were to look up silver and copper, silver plus 1 and copper plus 2, you would notice that silver is going to be gaining 1 electron per silver to form the elemental silver, and the copper is losing 2 electrons to form copper plus 2. So in terms of our electron count, there's going to be 2 silvers needing to be reduced for every 1 copper. How I know that silver is being reduced, well, this is the direction or the order that they wrote the equation in the first place. But if I look at the reduction potentials for silver plus 1, so this is for silver, that reduction potential from the chart that you have is 0.80 volts, and the reduction potential for copper, and again this is the formation of plus 2 copper, from the formation of plus 2 copper, you have 0.34 volts. So the fact that we say that this is a larger reduction potential for silver means that this will be the thing that's reduced, the silver, so that's going to be at the cathode, and the copper is going to be at the anode because it's going to be oxidized. So the thing with the lower reduction potential is going to be the one that's oxidized. Okay, so that being said, I can calculate the standard E cell. Again, in this original problem, if you actually look at it, they gave this to you, but the idea is that you take the potential at the cathode and you're going to subtract the potential at the anode. And the reason we're subtracting the potential at the anode is we want the difference between the two potentials. So again, what's happening at the anode is oxidation, which is the reverse of the way that this value is given to us. This is given for reduction. So just the subtraction of the anode gives us the negative sign that we need. So that gives us the 0.46 volts that they gave us originally in the problem. Okay, so that's E naught for the cell. And so if we're asked to find the spontaneity, well, we know that this is a spontaneous process as written because we're going to see the substance with the higher reduction potential being reduced, well, with the lower reduction potential being oxidized, and that's the way the equation is written. The fact that this voltage for the cell is positive, that's also how we know that this is spontaneous. And so we would expect when we find delta G naught that is going to end up being negative. And so the equation is delta G naught equals negative NF E naught for the cell. N is the number of electrons that is transferred. And so again, if I were to look at the half reactions, as I mentioned, the silver is going to have to be gaining 2 electrons for 2 of these ions to turn into 2 of those silver atoms, geez. And then the copper, to go from copper neutral to copper plus 2, is going to have to lose 2 electrons. So this value is going to be 2 for this particular reaction, and you can find that by looking at the balanced half reactions. The Faraday's constant, again, you might see it either as 96,500 or 96,485, but that's coulombs per mole of electrons. So that's the charge on a mole of electrons, and then we've got the E cell. So now it's just a matter of plugging in. So I've got -2. And notice this negative sign here. If the E cell is positive, that's how delta G is going to come out negative, as we said, for any spontaneous reaction. Again, I just plugged in the 96,500. Whatever's given to you for Faraday's constant, that's the one I would use. So, wouldn't worry about that. And then this is 0.46. And again, a volt is a joule per coulomb. So when this is coulombs per mole. This is moles of electrons. So the moles cancel, the coulombs cancel, and I end up with joules as a unit. So we're multiplying all that out, and it's negative 88,780 joules. Technically, since this has 2 significant figures, I should keep 2 on my answer. And then probably since this is such a giant number of joules, I would put it in kilojoules. So we would say that's negative 89 kilojoules for my delta G. Okay, so that is for standard conditions and delta G naught. So standard conditions being 298 Kelvin and 1 molar concentration. Let's take a look at problem C, which is if I have a cell constructed that has concentrations of 0.045 molar for the copper ion and 0.010 molar for the silver ion, calculate the potential for the cell. So again, they're giving us non-standard conditions for this next part. So this is question C on the sample problem worksheet. So I have 0.045 molar for that one, and I have the silver 0.010 molar for that one. Okay, so we're going to be using the Nernst equation if we have non-standard conditions. And the Nernst equation is, well, if we take what we know about the, delta G non-standard and how it's equal to delta G standard plus the log, or plus RT times the log of Q, that's what we saw in the thermodynamics unit. If that is reworked using these values for delta G naught, so delta G naught would be negative N FE, regular delta G would be negative N F with a non-standard E, and then again you can look at the derivation in the book. But if I wanted to find the potential of the cell at non-standard conditions, that's what the Nernst equation comes in for. Okay. So the Nernst equation, when it's all rearranged and plugged into, what it comes down to is, so again, this is going to be for the cell, non-standard conditions, taking the standard for the cell minus, and again, if this is at 298 Kelvin, this number that I have up here applies, because this would be like an R, a T, and N, and then Faraday constant. And for whatever reason, the convention is to, instead of dealing with natural log, they have converted that to the log of Q. So again, the derivation of this equation comes from that delta G equation for non-standard conditions that we saw in the last unit, that's just been reworked with the values and relationships we talked about in this unit. So I need to plug in here. The Ecell, we just found that, so that we said was 0.46. The N value, well, that's the same that we've already discussed for this reaction, that's 2. We can see that from the balanced half reactions before we added them together. Then we need the log of Q. Okay, so Q, again, is the reaction quotient. So with these concentrations, we're going to plug into the equilibrium expression, and that's where Q comes from. So with this equation as written, remember that, I should probably have these states of matter here, the things that are in solution, the ions, those are going to get into the expression, but we know that the solids that don't have changing concentrations don't belong in the expression. So my Q expression is going to look like this. I'm going to have concentration of products. There's no coefficient, so it's raised to the 1. And then divided by the concentration of reactants, so that's silver, and that's going to be squared because there's a 2 there. So then I'm just plugging in the values that I was given for the concentrations that I do have if they're not 1 molar. And so I have 0.045 molar divided by 0.010, and that is squared, so make sure you do that. That all comes out to be, where is it, 450. And so this is going to be the log of 450 that I plug in there. Okay, so doing all my magic in my calculator, I end up with 0.38 volts. Okay, so this ends up being 0.38 volts. What that means then is at these non-standard conditions, I end up with a cell potential that's less than I would have at standard conditions. And if I think about this, again, this is my reactant amount. I've got a smaller amount of reactant than I do product. And so that means then that, well, again, I've got less potential for that forward reaction, right? Because, well, I end up with a lower voltage, but my Q value is, well, we don't know what the equilibrium constant is, but my Q value is lower than it would be at standard conditions. And so as a result of that, I know that my, I'm getting a little bit less voltage here for my overall reaction. So there you go. That's finding the Ecell from non-standard conditions.